about the person Kravchuk. I wrote it like this. I found out by now that there's a preferred spelling which would be like this, Kravchuk. So who was Kravchuk? He was a Ukrainian scientist, a mathematician, born 1892, living through 1942. And this final year, 1942, probably already rings a bell with you that there was, in this political trouble. I found a line online describing this. It says, anyone knowing even a little Soviet history of the 30s can conclude that Kravchuk could not avoid the Great Terror. So this was the Stalin regime coming down on many scientists, and that included Kravchuk, who was, accused of being a spy in Syria and died, unfortunately, I think shortly before his 50th anniversary, his birthday. But then about these polynomials, I got a question yesterday that I'd like to come back to. I wrote things like this. I said there's Kravchuk polynomials k, n, k, x, which were the eigenstates of this xy chain, special couplings. So to recall, the expression was like this: j equals 0, minus 1 to the j, xj, and then n minus x, and minus j. So this hides a bit a polynomial of variable we are talking. So I found a more standard notation for this would be now the Kravchuk polynomial with index k, variable x, and parameterized by n as the size of the system. And this way makes it more clear that this is a polynomial in x. And if you actually check this formula, you can see this one has degree as a polynomial in x equal to k. So the leading term is to the k, and then there's more coefficients there. So that was a comment on these Kravchuk polynomials. Second, I got a question from Nigel, who said something funny. You talked about generating a rainbow state, let's say on n sides. So meaning that on an n-side chain, we could entangle massively the left to the right degrees of freedom via these arcs representing bell pairs between left and right. I gave the time to do this pulse only took time pi over j, with j some constant. It looks funny, right? Because this says that angle constant time, because there's no n in here, and that looks too good to be true. And the reason that this happens, this is against intuition, right? You would expect a time of order n to achieve an entanglement operation like this. And the reason this comes out this way in my formula is the couplings I'm showing myself. So these Kravchuk couplings, they're actually, they had this shape that they were weak at the ends and strong in the middle. And I give you a formula for what these couplings were. So this the Kravchuk couplings at x. But if you look carefully at the formula and you go to the middle of the chain where the coupling is strongest, so let's say x equals n over 2 or thereabout, then you can see that in this situation, so x near n over 2, the coupling actually scales like, I think it's j times n over 4. Again, couplings themselves grow with, and they're order n in the middle. And if I allow myself that, I can get a constant time. If I would reorganize that and say this has a max at some constant, and the time would pick up a factor of n as a consequence of that. So there's nothing against intuition here of how the conventions were chosen. Practical point, I made some notes of yesterday's lecture, so a short summary and some references, and those have been posted on the conference site. I also posted this demo in Circ that I showed yesterday, this bit of quantum code, so you can play with that if you like. And the third thing I put on the notes is some exercises. So based on yesterday's story, I made a few exercises that you can try your hands on. So please make a try for that. And we can discuss. For example, discussion sessions planned in the school. I think there's one this afternoon. We can talk about this and I'll give you hints and solutions and things like that. And I'll keep doing that. So I'll post similar surveys and summaries and exercises in each of my 5 lectures. Okay, so let me start a new chapter of my story. So that would be entitled Resonant Driving, where I'll add in the beginning that it could be resonant or it could be off-resonant driving. I'll discuss both situations. And you know, it's time we talk about this because in yesterday's lecture, I have quite a few examples of how you drive a qubit system. So to make a 1-qubit gate or a 2-qubit gate, pulsing some well-chosen interactions. So in particular, we looked at 2-level systems, and I told you that if you have an interaction, you know, like X, maybe like Bx times X, you know, with as a 2x2 matrix, 0, 0, 1, 1. If you export that for some time, so there's e to the minus I t x, say, there was this expression cosine cosine of t times identity minus I sine of t times x. Yeah, so we saw this kind of thing, and we noticed that if you have available this unitary operator and you choose your time smartly, like t equals pi over 2 in this case, with all couplings equal to unity, you know, you have a way to enforce a transition from state 0 to state 1. At this point, the unitary that's here is exactly this u of x is exactly equal to minus I times x. So that's all very nice. But there is one complication which I kind of avoided yesterday, which is that typically these 2 levels that you like to interchange are offset by some energy. Typically, there is an H background, say, to this whole process, which could be, let's say, it's delta over 2 times z, right? So this matrix here, delta over 2 minus delta over 2. So in many situations, this is the case. So these 2 levels that are taking the role of your qubit are not at the same energy. Now, if you have this background and you try to add this pulse like given here, it won't work. So it won't make a transition from 0 to 1. It will do some dynamics, but not the clean transition that you're after. And the reason is that, you see, if there's a background Hamiltonian like this here, there are oscillations, right? So there's an energy gap of delta between these 2 levels. And that means that, you know, your solutions to the Schrodinger equation are oscillating with e to the minus I delta t, typically. And this oscillation is in the way of this driving process. And the solution to still be able to do this driving is to actually make the driving term resonant with the, let's say, the eigen oscillation that the system likes to have. So that's why this thing is called resonant driving. So there's a frequency built into the background Hamiltonian, and if you tune your driving to be resonant with that, the whole thing will end up working again. So the proposal is that if this is your background situation for the 2-level system, what you should add as a driving term, you know, as opposed to what we did yesterday, is something like this here. So you give some strengths omega, and then, you know, you make a combination of x and y terms, Pauli matrices, which you give the right some frequency. So you say, I do cosine omega drive times t plus some phase, maybe, to be very general, and that I do times the x matrix. And I add a second term, sine of omega drive t plus phase times the y matrix, so the Pauli y matrix. Okay, so these will add off-diagonal terms to my total Hamiltonian. And the idea is that if I choose this omega drive wisely, I can enforce dynamics, which is still going to be of the driving type. Okay, so the little exercise is now to solve, you know, so the time-dependent Schrodinger equation for the total system, you know, H background plus H drive. So that's the homework. I mean, it's not very difficult. It's a 2x2 problem. So you can all do this, but let me guide you there. What is convenient is to actually solve this, do this analysis in what's called a rotating frame. So try to build in the expected oscillation in time into your wave function. So let's say your states, your eigenstates k, you typically like to look at some URF of these things and call this k tilde, where URF is a unitary that transforms you to the rotating frame. So it's going to be, let's say, e to the I times some h0 times t, where this h0 is going to be taken as an omega rotating frame. Same thing that's coming. This is a new choice here over 2 times the Pauli Z. Okay, so I go to a frame where I build in these expected oscillating factors. And what makes sense now is to, you know, to choose for this omega rotating frame the same frequency omega drive. Right, so there's an imposed frequency term, and you like to follow, you know, you like to use a moving camera, so to say, that's in the rotating frame. And by doing this all works, and you can, you know, rework the problem into this rotating frame variables. That gives you an Hamiltonian H tilde, working on these wave functions K tilde, which, to be complete, you know, it's the URF, and then it's the old H, and then it's URF dagger. And then because there's a time dependence in the U, you pick up minus H0 here. So this, you know, you can do on the back of an envelope and convince yourself that the proper Hamiltonian in the rotating frame is like this here. And now if we work all that out, and again, let me not go through all the details on the blackboard, I get a 2x2 matrix in the rotating frame. So the good thing, the off-diagonal terms are like omega e to the minus I phase, and down here omega e to the plus I phase. And on the diagonal I find delta over 2 with a minus, where this delta, you know, comes from 2 sources. First of all, there was this original background Hamiltonian with, you know, capital delta as input, and then there's this minus H0 that comes with the transformation to the rotating frame. So these things add up, meaning that in the end what's on my diagonal is delta over 2 with delta equal to the original delta minus the omega drive. Or if you wish, omega rotating frame, which is the same thing. Okay, and so now what this exercise has is that I'm back to a time-independent problem. So I've, you know, eliminated these time factors, and so now it's going to be very easy because this is an easy thing to solve. Okay, so this is quite standard, but I found I need to go through this because this will be at the basis of many of my tricks that are coming a bit later. So I'm now close to draw some conclusions. Because, you know, analyzing this constant problem is very easy. So first of all, you know, let's go on resonance. Yeah, so make a remark. So if you put delta equal to 0, so meaning that we tune the driving frequency to be equal to delta, that's the obvious thing to try. You know, I'm back to the old story on my top line there, because then it's down here, so I'm in a combination of driving with X and Y, and, you know, the clean driving without any complications. So delta equals 0, that's, you know, on resonance, resonant driving. And you can see that you can do a clean transition with time t equals, what is that? It's pi over 2 omega, I guess. Yeah. But also, let's also imagine, consider this case where delta is not quite 0. Let's write the general solution. That's not too hard. So let's do the u tilde of t for the general case. So which is e to the minus it times my h tilde. If you work that out with a bit of algebra, it's going to be cosine of n times t times identity minus I sine of n times t. And then comes, a combination of the Pauli's that from the mixing that I have here. This is like a mix of Pauli x, y, and together. So the combination that sits in the u is n vector over the length of that dotted into sigma. This n vector is cosine phi times omega, and then sine phi times omega, and then delta over 2. And the n that I put in my formulas is a frequency, and that is coming like this. It's the omega, the strength of the driving squared, and then the detuning comes in as well, delta squared over 4. So this is the grand formula saying this is what happens in the rotating frame, and then going back to the original frame, simply add these extra phases that are running along all the time. But now this formula is interesting, right? So if I put delta equal to 0, I'm back to what I said. So then the frequency this thing goes is omega sharp, and I have oscillation where I can play with x and y via this phase factor. But you see, if in the opposite limit, so I can consider the delta, the detuning, to be much bigger than the omega scale, meaning that I'm far off resonant, so I completely miss hitting the right frequency. And then you see the whole thing is going to be very different. First of all, this n is going to be much bigger, and second, the term that should be doing the flipping between the two states is now dominated by the third component here. This is the big one in this limit, meaning it's sigma z, meaning it doesn't flip at all. So it kind of, you'll do small oscillations, but you stay close to the original state, so you don't do any Rabi flipping at all, but you do a bit of wiggling around the original state. And you don't manage to do a transition because you're off resonant. Okay, that's the physical intuition. So no Rabi flops, if you wish. Now you can say this is quite useless because the whole game of the quantum game is to do transitions, but we'll see some examples where playing with this detuning, actually choosing that wisely, gives you all kind of options to do the desired physics, so to say. So in atomic physics, you think of lasers, hitting levels of atoms, and there typically you play with detuning the laser frequency as opposed to the system frequency to achieve certain effects that you like to have. But in all cases, you come back to this grand formula to understand what's happening and what you're doing, and to what extent states, or it's just small oscillations that don't do much. There's one thing I should still say. So what I've given you here is exact. So the algebra is I didn't give you all the steps, but I didn't make any approximations. However, in practice, if you do the driving, it's not always possible to precisely combine the x and the y terms and all the phases. So I made a certain choice here, which was essential for my algebra. So typically, you could imagine, for example, that you can only drive via the x term, and this y sine phi term would be absent. If you would try to do the same analysis, it would be similar but less perfect. In particular, I think in this diagonal spot here, there would be some terms oscillating with actually as frequency omega drive plus omega rotating frame. So these things wouldn't quite cancel as they did in my case here. So you could say, well, if that happens, is lost, then I'm in big trouble. But if you look at these terms, these are, e to the I t times, this is a very big frequency on the scale of my things. And it turns out that I can safely neglect terms oscillating that fast. They don't affect my final outcome by much. So that's called the rotating wave approximation. You typically do that because you trust that what you throw away there is a small correction. That's not very essential. But again, you should realize that there is this version with these two terms combined just right, where it's an exact expression, but in practice you typically have a less perfect choice here, so you have to make an approximation called rotating wave approximation, where you neglect terms like this, but the outcome is essentially the same. Okay, so much for this little piece of let's say, technology that's going to be needed in many cases. I think, most of the actual qubit driving things that you see in hardware are of this type here. There's always a frequency to be tuned. All right, so let me we keep this here for you to look at, make room on that side for a new story. So now, I'd like to come back one more time to these spin systems. I talked a bit yesterday about considering more than, so couplings not just of 2 qubits, but let's say of a whole chain, or at least more than 2 qubits. And let me play a bit with that, and let me give you a motivation why I do that. You see the whole purpose we're following is to, to realize certain quantum circuits that can do interesting quantum computations. Now, if you look at these circuits, so let me give a little bit of a heading. Let me call this part many-body strategies for multi-qubit gates, where I guess I need 2 hyphens. So that would be my little heading for what's coming. And again, the motivation is that if you look at circuits that are actually used for useful things like error correction or what have you, one gate that you typically see is called Toffoli. It sounds Italian to me, but that's appropriate. What Toffoli does, it's a natural extension of this C0 gate that we had. So if you wish, Toffoli is in shorthand, it's a CCC, etc. knot, where I control my knot with, let's say, n control qubits. So if you wish, in a circuit, I can draw n plus 1 qubit lines. Have a gate that looks like this. So I do a knot on the what's called the target qubit. Let me call it T. And then I have control qubits C1, C2, all the way to Cn. And I like to control my knot by every one of these control qubits. Right? So this is easily explained what this does. Right? It only acts. The only thing this does is that it sends the state, with 1, 1, 1, 1, 1, 0 to 1, 1, 1, etc. 6 here, 1, and vice versa, and leaves inert all the other states. Okay, so it's easily explained what this thing does, but it's a bit hard to actually have it. Now, yesterday I promised you that there is this perception that whatever gate I come up with, I can compile it in knots and 1 qubit gates. So I can apply the theorem to the situation, and I'm guaranteed that there is a solution. But it has been, this has been analyzed, and I think there is a can compile Toffoli, with n controls into C0 and 1-qubit gates. But again, it's a bit difficult. If I take the n equal to 2 case, so which is the first beyond the regular C0, so the Toffoli with 3 lines, I think it's been established that the number of C0s that you need in a circuit like this is at least 6. So there is actually a way to do this with 6 C0s, and I think it's clear that you cannot get away with less than that. If you make Toffoli n, it depends a bit on what you allow yourself. If you allow yourself ancilla qubits, so extra qubits to bring into the story, you can do it rather efficiently. I think order n depth. If you don't allow yourself that, it's even more difficult. So the morale is that you can compile Toffolis into C0s, of course, but it's an expensive thing to say. It's going to make your circuit pretty big. And so the idea has been, so the motivation of particularly my work with Koen Groenland, can we do better if we exploit many-body interactions? So this is a many-body dynamical process. What if we use smartly many-body interactions? Can we kind of shortcut this standard construction of Toffoli? So now we played with this and many other people as well. So I'd like to briefly report on 2 proposals for doing this. So let's say let me call this many-body shortcuts to this situation. So we proposed a few. The first we proposed is based on the Kravchuk chain. And the second is proposed on a thing we call the Ising star. So let me tell you about that. I think these are quite beautiful stories. It's a bit unclear if they are going to be, let's say, practical and help the actual technology along. I think this Ising star probably for the Kravchuk chain, it's difficult, so you need somebody to build a perfect Kravchuk chain in the first place. Let's see what is possible if we would do that. And mathematically, this is quite an intriguing story that is kind of nice. So I'm returning to my Kravchuk story now. So new chapter. So this is about resonant driving. On Kravchuk chain eigenstates. And I prepared quite a few things yesterday, so now this is a relatively easy story to tell. Let me recall. So there was this Hamiltonian HK. So just to be sure, it's minus, it's the sum of axes of these jx over 2, and then it's x plus 1 plus yx plus 1. Yep, and I gave you yesterday this jx expression. I'm not repeating it here. And we learned yesterday that the energies for this E sub k are this very simple linear shape. So there was this j in front, and then it was k minus n over 2. And I could run k from 0 to n, because I agreed that the chain has length capital N, which is small n plus 1. But that was yesterday's story. Now let's play a bit. I'm going to define a second operator, call this hz, which is a much easier operator on my chain. It's going to be j, sum over x, 0 to n, so I sum over the size of the chain. I put, the counting operator, so if it's 1 minus zx over 2. So this is the same if, I could write this as nx, right? So it's 1 if my state is the bottom state, the 1 state. It's 0 if it's the top state. So it's just a counting thing. And then I I give this a weight, x minus n over 2. So this is, you know, a diagonal Hamiltonian, so I can diagonalize it with my eyes closed. And the eigenvalues, let me call them fk or something, fx, say, are j times x minus n over 2, with x equals 0 all the way to n. Okay, easy. But now you see, you know, this is on purpose. These expressions are identical if I go from k to x and x to k by construction. And this suggests that I can maybe, you know, do a transformation where the eigenstates for this h of z, which are the simple. So the eigenstates, just to be sure, here I can actually write them immediately. Eigenstates. I would write them as x. So let's say the state is one spin down and all the rest up. And what I mean by x, you know, it's the bit string 0, 0, 0, and then a 1 somewhere, and then everybody 0, 0, 0. And the 1 I put at position x. So the computational is at the same time my eigenbasis for this. The eigenstates over here, just to be sure, they are non-trivial. And, you know, they involve these Kraftchev polynomials that I talked about yesterday. So we can write them, but they're non-trivial animals. Okay. So clearly, mathematically, there is a unitary transformation sending my basis on the top to my basis on the bottom. These things are typically hard to control, but in this case, it turns out we can quite easily find a unitary that does exactly this basis transformation, which is kind of surprising. And to give you a bit of intuition of how we find this thing, let's do n equal to 1, meaning n equals to 2, capital N, so the two-side chain. So the energies in this case, so the EKs are, you know, if I mod out a factor of j, they're plus or minus half. Well, let me mod out a factor of j over 2 actually. Sorry. So this is, the energies are j over 2 times plus or minus 1. And the f-axis are also j over 2 times plus or minus 1. And if you write these big Hamiltonians in this very simple situation, you'll find that hk in this case is simply the x operator, the Pauli x, and hz is simply the Pauli z. And, you know, up to a factor j over 2, and that works with these eigenvalues. So in this case, I'm down to Pauli x, Pauli z, and then we know how to do it, right? Because two facts about this. Yesterday I told you that if I do Hadamard times x times Hadamard, it gives me z, and vice versa. So Hadamard, just recall, Hadamard was this thing, 1 over root 2, 1, 1, 1, minus 1. There's another fun fact, which I didn't give you yesterday, which is actually subject of one of the exercises, and that's that I can express h in x and z in a funny way. Namely, if I do this here, square root of x, square root of z, square root of x, those are all 2 by 2 matrices. You can check that this is actually giving you the Hadamard from the x and the z operators. Okay, so for n equals 2, that's how we can do things. And we can go from one basis to the other as we go. So now the amazing thing about this Kraftchev situation is that for n sides, the algebra underlying the left two bases is identical to what happens for n equals 2. So what I can do, I can write a unitary UK, which is pretty much root x, root z, root x, so in the sense that I do, you know, e to the minus I pi over 2j times hz. Okay, so this would be the analogous thing to writing actually square root of z. So sorry, I should have. So there is this duality, right? So this is true, but there's not so true, which is this. Believe me, as I do. So and this is the one I'm actually generalizing now. So I'm writing, as opposed to square root of z, I'm writing this thing here. So the hz with this pi over j just for normalization. And then I put this half, which represents the square root. And then I put e to the minus I pi over 2j h Krautchuk, which is the thing akin to square root of x. And then I put another e to the minus I pi over 2j hz again, which is akin to square root of z. And now comes the nice theorem, which is quite interesting. If I do hk times uk, it's the same as uk times hz. So my uk is the intertwiner between these two bases. In the similar way that h, the Hadamard, was the intertwiner between the two bases in the baby example with only two sides. Okay? And so in our paper where we found this, we call this uk an eigengate, which I think is a new word in the English language. An eigengate, because what it does, it transforms the computational basis, which we have available at start, to this non-trivial basis. In a sense, it spits out the Krautchuk polynomial, which is, I think, very nice. So this is a quantum circuit that spits out Krautchuk polynomials. In a single pulse, well, a single composed pulse, right? I have to turn on hz for a bit, hk for a bit, hz for a bit, and that's it. So if I can do that, so if I have a system with n qubits coupled in this fashion, I can pulse 1, 2, 3 operators, and I spit out my Krautchuk polynomial basis. So I think that's quite remarkable, and it can probably be used for all kinds of things. So the use I have for it today, I'm going on this side. So so let's explain my proposed protocol. So let me summarize what I have there. So I can, so the computational basis. Which I'll denote as, this. So I give examples with a single x, a single overturned spin, but I can do many of those. So then I have a collection of x's, so let's say x, xj or so. So the entire Hilbert space has this basis. The eigenstate basis. So the HK eigenstate basis. And for those I use the case, right? And I can put many case to put many of these Krautchuk polynomials in action. And so we learned now that we have a UK that goes back and forth between these two things. And that we can make in a circuit if we have control of the Krautchuk interaction. So that's nice. So let's let me propose a protocol. So to run in the lab if all this is in place. So what we have, so step 1, we start from some computational basis state, one of the X states. Step 1, apply UK. Step 2, do a resonant pulse. So like on my previous chapter, that I'm going to tune a frequency to be just right, and this will be from, let's say, the lowest to the highest energy state in my many-body spectrum, and then step 3, apply UK inverse to back to the original basis. So let me explain my protocol in the case n equals 4 to make this not too complicated. Let's do it in n equals 4. So what are my energies in both of these bases, the eigenvalues? Well, there was this j, and in this case, you know, I have minus 3/2, minus half, plus half, and plus 3/2. So those are the one-body energies that are, they were some on the blackboard before. Now let's do the full spectrum of, let's say, the Krautchuk problem. Full spectrum. It's a free problem, so I can, you know, load excitations with these energies. So now I have to make a picture, which is a bit hard on a board without grating. So this is, you know, state I have. State with, I can put a single excitation and I get energies: 3/2, half, minus half, minus 3/2. So for example, this would be the 1, 0, 0, 0, right? So I load this one. This would be 0, 0, 0, 1, etc. I can put two excitations, then I go down to minus 2, minus 1, 0, another 0, plus 1, plus 2. So from down here would be 1, 1, 0, 0. This would be 0, 0, 1, 1. And then I can keep going, 3 body states, and there's 1 4-body state. Okay, so these are, sorry? Sure. Maybe they can type it.
Unfortunately, maybe, yeah. Can you repeat it, because we have a problem with the audio in the room, so maybe Kareljan, maybe you can come here.
Okay.
Can you take this and try with that?
Yes. I'm just. Yeah, that's correct. Okay, thanks. Yes, it was indeed that the level over here, the zero energy level has you know, no excitations loaded, so it's simply zero energy, etc. So this would be 1, 1, 1, 1, right? Everybody loaded, and then the energy adds up to 0 again. So this is the Krautchuk spectrum. Again, each of these positions, you know, is a interesting product of a bunch of polynomials giving the one-body wave functions, and the energies are like this here. Okay, so now comes the trick. So in step 1 of my protocol, I map my computational basis to this basis. Step 2 is now that I'm going to do a resonant driving. So what I'm going to do, I'm going to apply some kind of pulse to the system, for example, by kicking a few of the spins with sigma x, say. I'm going to make it resonant with this energy over here. So if you wish, this energy jump is in my units, it's 4, right? So this energy is like plus 2j. This energy down here is minus 2j. So I'm going to make a resonant pulse, if you wish, you know, the omega drive equal to 4j. So it's resonant with this transition, and since there are no other transitions with 4j energy, I'm leaving all the rest alone. So for driving like this, everything is off resonant except this one possible transition. Okay? So what I can do, if I leave this pulse for just the right amount of time and wait a bit, all the states they put, except for this one here and this one here, they will, you know, change places. And in particular, if you look carefully, what will happen, you know, the 0, 0, 1, 1, if I do this right, will go to a factor of I times 1, 1, 0, 0. And 1, 1, 0, 0 will go to I times 0, 0, 1, 1. And all the rest will stay where they are. So that's that. And now, so and this notation is in energy space, so these are K labels. But I can do UK inverse, and then I go back to X labels, right? And I'm back to the computational basis. So in the end, my whole protocol has achieved this thing here in the computational basis. So it's a multi-qubit gate that leaves the basis of 2 to the n states in place, except for this one swap here. Roughly, because it's off resonant driving. So if you wish, it's my previous chapter with a big detuning. So there's what's AC. Yeah, it's not exact. So there is a fidelity issue. You can actually see if you do this exactly, what the fidelity actually is, and there is a bit of imperfection because the resonant driving being off resonant. But yeah, so this works quite well. Certainly on paper. Now, this a word on this. This is not Toffoli, right? Toffoli was another operation that leaves everybody in place except for 2 states. So there is a bit of work to kind of translate or compile this thing here to the Toffoli version. And actually, if you do that, I think the best way we found is to use one qubit as an ancilla, so like an auxiliary qubit. So I think if we do this whole thing on 4 sides, it allows us to make the actual Toffoli gate with 3 sides. So meaning 2 control qubits, 1 target qubit. And in general, so our claim is that if we do this procedure, so the protocol, let's say, on n sides, allows us, via a bit of compiling, to do this Toffoli gate on, with n-2 controls and 1 target qubit. But you see, the thing is quite fast because the basis transformation is this pi over j time. The pulse is again a pi over j time, and going back is again pi over j. So the quality of this protocol is limited. There is the same factor of n that I mentioned in the beginning that is a bit hidden in the Kraut-Tube couplings. But for the rest, this is an interesting idea of building a Toffoli gate. Okay, so I'd like to leave this topic with that. So there is this paper that Groenland and I wrote where we give many more details. I mean, there are issues, right? For example, I wasn't quite clear about how this driving goes. For example, one way to do it, if the chain has an odd length, you can simply take the middle qubit, put a sigma x on that, give it the right driving frequency, and there is a matrix element between these 2 states, so it does the job. But then if you look at that matrix element as a function of the length of the chain, it goes down very, very fast, exponentially fast, which means that the protocol becomes quite inefficient and quite slow for long chains, right? There was this omega in my driving story, that omega tends to go down with n very fast, which makes this whole thing impractical if n is more than 10 or so. Which is one of the reasons we looked at yet another proposal for a similar game. And so I think I can maybe still do that, and then maybe we should break now, right? That's more according to custom. Yeah, so let me stop here and start a new chapter after the break.
As far as I remember, Toffoli gate was invented, let's say, was introduced to solve the paradox that classical quantum computation has irreversible gates, while in quantum computation, being a unitary, you can never be irreversible. Is it true?
I think you're right. I don't have the details in my head, but yeah.
So I mean, Toffoli thought how to solve indeed this clash. I mean.
Yeah, of course. There is this issue. In the context of quantum, everything is reversible by definition, right? Everything is unitary and reversible. So for quantum, it's just one of the gates we like to have in our hand. Yeah. Yeah, let's then break and be back in 10 minutes or so.
Yes, 10 minutes. So at 11, so 9 minutes.
Yep. So I think it works, right? Okay. So let's continue second part of today's lecture. Another proposal for a resonant driving scheme to do multi-qubit operations. I think this one is a bit more practical than the previous, less involved mathematically, but still. And what I do is I do this, what I call Ising star eigenstates. So what is my Ising star? Let me draw you that. I imagine, what I'm after is again a Toffoli type gate with n controls and one target. So let me assume that the qubits that I'm going to talk about are laid out in a kind of star configuration. So there's a center where there's qubit number 0. That's the target. And then let's make a star of, in this case, 3 qubits. So let's say there's 1, 2, 3, like this. And then let's assume we can do 2-qubit couplings. In this case, let's assume we simply can do them on the graph that's drawn like this. So this would be an n equal to 3 situation, n equal to 3 target qubit. And now let me add what I assume in terms of control or energy terms in the situation. So first of all, I'm going to assume that there's an overall sum over all the z's, so the Pauli z's. And for simplicity, take all these omegas the same, but you could play with that. Next thing, I'm going to assume that all these lines are 2-qubit couplings, and I'm going to assume that they're all the same. So this is what I call coupling, right? It's then you could do xi xj or zi zj. So let's assume that, and again, it sits on all 6 legs of my picture. And then the third thing I'm going to assume is that I'm driving the central qubit, so the number 0, the target qubit, with a term, let's call that. And I'm assuming on that. So I'm putting this x field on the middle qubit, and I give it a frequency, anticipating that I can set up a resonating scheme to make things happen in this configuration. So this is my setup. I'm assuming somebody arranged all these couplings, and now I'm going to see what that does for me. So if I start in, let's say, a computational basis state, and I let this thing on for a while, what will it do for me? Let's go to this rotating frame. I'm going to apply the technology that I lined out with this resonating driving, resonant driving. So rotating frame. I'm going to have a Hamiltonian, so I called it H tilde a bit ago. Let me do that here as well. It has the following terms. Right? So first of all, there's this omega 0 over 2 times z, which from there, zj, sum over all the j's. But in the rotating frame, there was a subtraction. So I picked up a z term with driving. In this case, will be omega g. So this will be correct to look like this. So that's the diagonal Hamiltonian. Then I have this sum I smaller j of the Ising terms, j z I z j. And then I still have the resonating driving, but since I'm in the rotating frame, I lost the cosine term. And I have a constant x0. By the way, if I do this literally, I need this rotating wave approximation to suppress a few more terms that would be rapidly oscillating. But this is the good approximation. So now let's look at 2 particular states. So in particular, let's look at the state, target at 0 and everybody else, the controls all at 1. And that's energy. So it's actually an eigenstate of this Hamiltonian. If you do a bit of bookkeeping, you'll discover the thing has energy E0, which is omega 0 minus omega g over 2. So that comes from this here. And it's a 2 because, there are 3 times a minus 1 and 1 times a plus 1. So that's this. And then the interaction turns up to, I think in this case, j times, and then there's minus 3 because there's 0 versus 1 on the star legs, and there's plus 3 because the outer legs all agree, the outer qubits. So that's this. So this is the energy, term. And then there's another where the energy E1, that's minus 4 in this case, of the diagonal, minus omega 0 minus omega g over 2. And now the interaction energy is everybody plus, right? Plus 3, plus 3. So that's easy algebra. So what I have for the diagonal terms is that, there's this gap E1 minus E0, which is delta E, so to say, which is omega g minus omega 0 plus 6j. Yep. So that's what I have. Now there's this, the extra term that I have here is the driving term. If I'd like the thing to be nice and clean, I should go on resonance, so let me assume that. So let's go for, delta E equal to 0, which means that I have to tune my omega g, which is that's the thing I control, right? That's the frequency I impose on the target qubit. That if I tune that to be omega 0 minus 6j in my example, then I'm on resonance. This whole delta E term is going away, and then I have a clean driving with this driving term x sub 0, right? Because x0 clearly connects these two states. So in this situation, what I have is, I have a sort of a clean, resonant driving. And what it does, if I take my pulse length just right, so some pi over whatever, g over 2, what it does is it sends, the state 0 and then 1, 1, 1 to, I guess typically minus I time, or maybe, well, that's minus I, 1, 1, 1, 1, and it sends 1, 0, 0, 1, 1, 1, everybody 1, to minus I times 0, 1, 1, 1. Now there's, many more states in my story. The whole thing has 16 states, but you can check that there are no other resonant transitions. So there's no other pairs of states that are split by exactly this amount over here. So this means this is the only thing that happens. Everything else is off resonance. Okay? So this situation, is quite a bit easier than my Kraftwerk scheme. I don't need this UK, because in a sense, my computational basis is by itself the energy eigenbasis, because it's all Ising couplings. So this scheme is much, I guess, more realistic, but it has the similar philosophy. And what it makes for me, is this gate here. Now this looks a whole lot like a Toffoli gate, except that it has these eyes here. And now you could say, well, these are overall phases, but they're not, because everybody else, let's say 0, 0, 1, 0 goes to itself, right? 0, 0, 1, 0. So there's no I here, but there's an I here, which means that this gate is not quite Toffoli. So this thing in our paper we call this I Toffoli, like we had I swap yesterday. And it's a detail. So if somebody likes to build a circuit that has a Toffoli doing a certain task, you have to consider if I Toffoli can be used, or if you have to do a bit of compiling around it. But it is, a gate that is very similar in spirit. And you see this way, it's generated in quite a realistic fashion, right? So in particular, so in the paper we wrote about this. This is, you know, again with Groenland and with colleagues in Aarhus, Rasmussen and colleagues. In that paper we work out this whole thing for n equals 2 or n equals 3 in the case of superconducting qubits, so transmons or gmons. Now, and we believe that for that situation, this is a realistic option to have. Another piece of work, which is a follow-up paper I did with colleagues in Amsterdam, is to do this scheme for the trapped ion configurations. I think I mentioned yesterday that trapped ions typically come with Ising couplings. They also come with all-to-all couplings. So in that architecture, this whole thing is quite natural. And it's, I guess it's now like a serious proposal in the trapped ion situation to use this scheme to generate your I-Toffoli gate. And again, it's in the spirit of using many-body things if you can, right? If you manage to arrange couplings like this star picture, you know, you can use that and make quicker schemes to interesting quantum gates. Yeah, I mean, there's details to this story, but I think this is maybe a nice place to leave it. What I prepared for today is one more chapter to the story where I'm going to make a switch away from spin systems. So, you know, we talked quite a bit about spin systems, about driving 1-qubit gates, compiling this qubit gate into native gates, and then today these two examples of a many-qubit scheme based on spin systems. Now let me bring up another type of, let's say, hardware that is extremely useful for all kinds of schemes for quantum simulation and quantum computing. You know, I'm not going to be complete. There is at least 5, 6 different physical systems that you know are considered for these purposes. So I'm not going to say much about superconducting qubits, trapped ions,
Kareljan,
photonic schemes.
So there is a question.
Yeah.
Could you comment what happens when there is some disorder in the couplings J, as is expected in experiment? What happens to the fidelity of the gate?
Okay, so if there's disorder in the J's, I think, you know, if I assumed all my J's and all these omega one-body terms to be identical. That's not essential. So if all J's are different, but we know what they are, we can still do this. And I think the scheme is essentially the same. Of course, if there's actual disorder, so we... no, I think that's the answer, right? So if the J's are set to a fixed value and we know what that is, we can do it. So the scheme is rather forgiving in that sense. The Krautchuk scheme is not very forgiving because it needs all this tuning to have exact UK gates. This scheme is rather forgiving for couplings not being the same.
Okay, thank you.
Okay, so as I mentioned, next to the spin systems, I'd like to bring up one type of hardware and play with it, which is what is, you know, in short called Rydberg atoms. Which I think is a bit of a... I think it should be called... where we consider Rydberg excitations as part of our story. So you've probably heard, you know, in quantum mechanics class about Rydberg states. So, you know, there's a principal quantum number if you do, let's say, your hydrogen atom. You know, n equals 1 is the ground state, n equals 2 is the first excited state. Rydberg states are, you know, excitations of atoms with very high principal quantum number, you know, maybe 50 or 100 or so. That means that in Rydberg states, the electrons are quite far from the nucleus, And it also means that atom-atom interactions are way stronger if the atoms are in Rydberg states as opposed to being in low states, like ground states. Okay, so what we typically will consider is, some that is, suitable for being controlled. So rubidium is an example, strontium, ytterbium, this kind of alkali atoms, for example. I guess there will be typically two situations where we consider, let's say, a ground state level, so a low-lying level in the atom, which could be the actual ground state, and then one of these Rydberg levels high up. And so this is like two levels that you can play with. View it as a qubit if you wish. Another situation which we will consider is a situation where the ground state is actually, split. So, for example, there's a G1 and a G2. For example, there's a nuclear spin in the ground state that is non-zero. Then there's a Rydberg level somewhere high up. And we are going to, so again, in the left situation, you can say this is like a qubit, and you need to control transitions to and from the Rydberg level to operate that system. In the second setup, the qubit would be, let's say, the G1, G2 combination. And the Rydberg level would be used as an intermediate state. So, for example, you could make G1 and G2 talk to each other via the Rydberg excitation. And that will be a scheme to play with. Actually, mentioning my options, a system that I will bring up in some detail, I guess, is one of these atom situations where there's a Rydberg level, there's many of them that we work with, and then the ground state situation is actually a system where we have G1 all the way to G10. So this is a case, so in strontium it so happens that one of the levels you can work with has nuclear spin equal to, so nuclear spin, let's say S equal to 9/2. Now if there's a spin S, you have 2s+1 states in the multiplet. So if S is 9/2, you have 10 states. So a strontium atom can provide that situation, which would be, let's say, a Q-dit with d equals 10. Which kind of comes to you because of the way this atom is built. And again, if this is your system, you're going to make these 10 qubit states talk to each other, for example, via this Rydberg excited level. And the reason we consider these levels, again, if I imagine doing some kind of quantum information processing with atoms, so there's one sitting here, sitting here, for example, confined using an optical lattice, or maybe using optical tweezers. So these kind of tweezers of light that can trap atoms. If it's just ground state configurations, they don't talk to each other at all, right? So they have van der Waals interactions, which are extremely weak, and unless if you put them in optical lattices, they can be so close via van der Waals, and you can make things work with that. If you put them in optical tweezers, they're typically so far away that they're completely inert, which is also a good thing because it means they don't decohere, but they're all by themselves. But then if you add them to their Rydberg states, they become much fatter, so to say, and they do talk to each other. And so that's the 2-qubit gates, so to say. If you imagine an atomic system, you always via Rydberg. So if this guy is excited, and this to, you pick up a considerable interaction, but only in that situation. And then you make atoms communicate in this setting. So it's a bit cumbersome, which means that 2-qubit and more qubit gates are a bit slow and difficult. But on the other hand, this atomic setup, is extremely good for having low decoherence. Right? These are atoms in vacuum. They don't do anything, as opposed to, let's say, superconducting qubits, which are in a solid-state environment where there's lots of noise and decoherence around. Okay, so that's a bit of motivation. Now, what is the, let's say, the theoretical description of, let's say, let's do a single let's do maybe 2 Rydberg atoms or a bunch of them. There's kind of a master Hamiltonian that everybody writes and that I'll be using as well for my story. It has the following terms, so let me write them and then give you some explanation. So first of all, I'm going to do a driving term in the same spirit that we had earlier today. There'll be this detuning term, and then there will be the interactions. Let's say I smaller j of some Vij potential, and then it's Ni Nj. So this is typically the Hamiltonian I'm assuming. So I should explain what this is. I'm referring to, let's say, the first situation. So with a single ground state. I keep the rest for later. So my situation is every atom looks like this. There's a ground state which I call Gi. It's almost the same as GGI, but then here it stands for ground state of atom I. And then there is Ri, which is Rydberg level I of atom number I. So this is my my setup, and I have a bunch of these atoms at locations somewhere so that they start interacting. So now what is the sigma x? So let me write what is Ni. Ni is the counting operator for the Rydberg state of number I. So it's this thing, if you wish, bracket notation. So it simply counts if the number I atom is in the Rydberg state, yes or no. The sigma x for atom I, that's the flip, so it's the operator that sends Gi to Ri, or vice versa. So this thing we call X all the time, right? It's the flip, the transition. And what else do we have? So these are I guess the quantum observables. And then there are these things, these coefficients. So omega I. So that is I guess the strength of the driving that you impose. Strength of driving. So the idea is that you hit a laser on this atom that has a certain intensity, and that sets this omega, the intensity of the term right here. Then, of course, the laser has a frequency, and you're going to make that close to this transition frequency that sits over here. But you do allow for a bit of detuning. That's this delta. So delta I is the detuning. So if you wish, you could imagine that your laser hits, for example, this energy, and what you miss would be this delta. The detuning, and again, it's sometimes convenient to make this delta non-zero, as we will see. And then finally, there's this Vij that's given by nature. So that's the way these Rydberg excitations talk to each other. So I told you if I put atoms both Rydberg excited, they do feel each other, and there's this potential that describes that Vij, van der Waals interaction, which has some strength C6. And then it has a dependence on distance, so let's say xi minus xj. So these are positions of these atoms, distance to the power 6. So it falls off very rapidly, but 6, grows very big with how high the Rydberg level sits. So if I think we consider n equals 70 or so for rubidium, and for that, the C6 is a sizable number. So that if you put atoms quite far away, maybe a few microns or so, you can still bridge this with this Rydberg interaction term. You see, there's no ground state to ground state interaction term. That's what I mentioned before. If they're ground state, they don't talk to each other. But both, so if both ends are 1, means both atoms are upstairs in the Rydberg state, they feel each other with this Vij over here. Okay? And this is all you have. So this is my Hamiltonian. So clearly this is like a cartoon of the actual atomic physics of these atoms, which is extremely rich. There are many more levels and there's many more details. but for, you know, my poor man's analysis as a theorist is based on this Hamiltonian here. So yeah, that's the Hamiltonian. Now let me the basic some basic physics of what's going on here and how this interaction actually happens. It's beautiful. So suppose two of these atoms next to each other. So here's atom 1, say it has its ground state and Rydberg state. Here's atom 2, it has its ground state and Rydberg state. So this would be G1, R1, R2, G2. Okay, now let's imagine we're considering our one atom, and let's imagine, you know, this one here sits in its ground state. And for example, let's put, you know, the detuning of the way we drive atom number 1, let's put it to 0. So let's go on resonance. Okay, so in my Hamiltonian, I drop the middle term. There's no term to the right because the end of the second atom is 0. So that term goes away, and I'm left with a Hamiltonian that simply says I'm driving with a sigma x on the first atom, which means, you know, I'll drive from G to R, R to G, etc. So I get, you know, clean Rabi oscillations, Rabi flops. So this is like a school example of my resonant driving story that I opened with today. Okay. However, suppose now that you know, our second atom is elevated from G to R. And that's, the situation is like this now. And let's again consider what happens to the left atom. What you see now is that there is a term, you know, which is this V12 over, let's say, the distance R12 to the 6, you know, which is multiplying N1. So in a sense, this is like an effective detuning of atom 1. Right? Because this thing, since N2 is equal to 1, this multiplies N1, so to say. In the, so it multiplies N1 and 2, and since N2 is equal to unity, it multiplies N1. It looks a whole lot like the detuning term. So although I agreed on a 0 detuning for atom 1, I still end up being detuned because atom 2 is, first of all, in the Rydberg state, and second of all, close enough for me to feel this. So now when do I start, you know, noticing the effect of this second atom? Well, as we see in the driving business, what matters is the relative strength of the detuning versus the driving strength, right? So there's like a sort of a critical moment when this VNN, well, yeah, so the V12 over R12 to the 6, let me call that VNN. By the time this becomes comparable to my omega on the first atom, so the way I drive the first atom, you know, that's the moment when the driving goes off resonant, right? We learned that we have to compare detuning with driving strength. If detuning is very small, it's resonant driving. If detuning has the upper hand, it's off resonant. When this condition is met, my first atom is detuned by so much that this whole Rabi oscillation business stops. And I can no longer excite the first atom to the Rydberg level. Okay? So, and now you see that I'm sort of doing a 2-qubit gate, right? Because if my right atom is in the 0 state, I can do a Rabi flop. If my right atom is in the top state, it's blocked and nothing happens. So it's like a controlled Rabi flop, which is almost the same as a C0. So that works. And now when does it happen? This here, now, you know, we can put in numbers to see what this means. Clearly, this means that I have to be close enough with my atoms for this identity to hold, because the left-hand side is like 1 over R to the 6. And now to give you actual physical numbers, I hope I got those right. So what this condition sets, like a critical distance, it sets what's called a radius or a distance. Let me call it maybe radius. No, let me call it distance maybe. No, let me call it radius. I think that's a more standard notion. A radius RB, where B stands for blockade. And that's the moment, when my there's like a blockade radius around atom 1, and if atom 2 comes inside of that radius, the blocking starts happening. Okay, and I can compute that number by working out this condition based on actual physical numbers. And so what I looked up, if I do an 87 rubidium atom as my atom species, I pick for my Rydberg level, just to be very concrete, and if I drive with an call, which is like megahertz, so these are kind of the numbers that come into this R sub B comes out as 9 micron. So just to give you a taste of the actual physics of these things. So this means, roughly speaking, if I keep this separation well above this 9 micron radius, the atoms are essentially not seeing each other at all, not even in their Rydberg states. But if I go below, so if I move atom 2 inside the Rydberg radius, the blockade radius of atom 1, I have this mutual blocking of excitations. And this is the secret, right? This is how atomic quantum computers work. They exploit this phenomenon.
Sorry. Why is megahertz and not gigahertz? Because it's atomic transition.
Yeah, but this is not
small.
This is not this frequency, right?
Yes.
This is not this frequency. This is the strength by which you drive the transition. So it's like the Rabi oscillation frequency.
But this oscillation from the ground state to an excited state.
Yeah, but there's sort of two frequencies to that. So one is the frequency set by this distance here,
Yes.
which I called small omega earlier on. But then there is this omega, and if you take this, small, it means the Rabi oscillations are very slow. And if you make this big, they're very fast. But that's like an independent choice you can make.
Ah, okay. Okay.
Yeah. And it's normal that this is way below these intrinsic frequency scales. Okay, so I'm. Is that clock accurate or? Oh, yeah. Sorry, I have a bit of time, right? Yeah. So this is what we can be exploiting, but there's actually a number of ways people have devised schemes exploiting this Rydberg atoms. And I'd like to give you this list of kind of 3 regimes that you can be in to work with these things. So this is, I'm deferring talking about, let's say, quantum gates in more detail for later. But there's these 3 regimes that you can consider based on that Hamiltonian. And they each come with a nice name. So first of all, we can consider a regime where all tunings are way below this omega. Let's say for every atom. Yeah, and where at the same time my let's say well below this Rydberg business, this Rydberg radius. Okay, so that's a choice I can make, right? So I put my atoms, for example, I put 2 of them, I put them relatively close, so way below this 9 microns. I'm going to take 0 over a small thing that's intrinsic, and then I pretty much have the situation that I just described to you, right? So this is the situation where if I first excite 2 level Rydberg, then number 1 can no longer do that, unless I completely change my laser frequency on number 1. So this is what's called the blockade regime. If you wish, what is available to you in this situation are, let's say you can do GG, you can do GR, you can do RG, but that's it. If you try to excite from, let's say, GR to RR, it won't happen. It's blocked by the other atom being in the Rydberg state. And this is, so if you if you build, for example, atom chains like people do, in this regime, there's interesting constraint dynamics because these RR nearest neighbor states are forbidden. So I'll come to that. There's the famous 51 atom chain of Lukin et al., where they are in this regime and where they see PXP models and quantum antibody scars and things. That's this story. There's a second choice I can make, which is different. So there is this VN. Let's do two atoms, like here. So there's a certain distance, and that sets this interaction to be a certain number. And now I can tune things such that this is actually going to be minus delta. So I assume a negative detuning, and I tune things in a funny way so that VNN and delta are essentially the same. And then I assume that VNN is actually way bigger than omega. And so again, I'm in a delta negative regime. So that's a thing I can quite easily arrange. This is called the facilitation. See what that does to let's say our two bodies. Well, we do this. Yes. Our situation, Rydberg. So let's get the terms in our Hamiltonian. Yep. So okay. So in our Hamiltonian, so we have this delta n, and both n's are 1. So we have minus 2 delta from these n terms, and then I have the VNN one time, which is again minus delta. So I don't want this. Sorry, I have 2 delta from the n's and minus delta from the V term. And it's a bit confusing. Delta is negative, and this is what I get. So I have energy of delta. If I do RG, times delta, and I don't have the interaction term because there's only one R. And if I do GR, I have the same situation of again the delta. But if I do EG, then I have. So now what you see is that 3 of my 4 states are at the same sort of energy in terms of this offsetting business, and the number 4 one is off. And since I'm assuming that my driving is very small as compared to this delta scale, I can never bridge that gap with driving, right? So if I'm in GG, I stay in GG, and I can't get out. But if I'm in one of the other 3, I can drive back and forth. So this is another kinematic regime where I have these 3 guys active, but I'm missing out on the GG one. And so it almost is a metric for only 2 atoms. Or if you make a chain, for example, and you put it in the facilitation regime, you get a funny, interesting constraint dynamics. I think I'll make an exercise for you to work that out. So there's a story about a fixed number of clusters of R's in the middle of G's. That's a conserved quantity, and that gives very simple constraint dynamics. So that's a nice regime to play with. And then finally, there's a third regime, which you can again achieve using these networks. So there's a third regime where, let's see, what I want now is 2 atoms again. I'm assuming that my omega i's are way below delta. So I'm again off resonant. But I'm not even assuming this kind of facilitation thing over there. Right. Yeah, so I'm staying away from that condition. So I'm simply going off resonant by quite a bit. So you could say, well, if you're off resonant, everything stops. But now I'm going to be interested in sort of the remnant of, let's say, the V of R 2-atom interaction. if I'm far off resonance. So my idea is now the following: I have my atoms that are pretty much in their ground state, meaning they don't feel each other. However, there is a bit of driving present because there are omegas, be it that they are small, which means that my atoms migrate to their Rydberg state and then they start feeling each other. So what this does, it gives, this is called the dressed regime, the regime of Rydberg dressing, which is like a sort of an, I would say like an induced G to G interaction. If you wish, mediated by the Rydberg levels. Okay, so this is a different physical regime, but it is one that is working for you. At least we had one situation where we make a proposal that's completely based on this situation. My final word for today will be a little derivation to derive this induced interaction when I'm in this situation here. So let me give you my Hamiltonian. So there's omega I over 2 sigma xi, so I call my atoms I and j. Omega j over 2 sigma xj. Now there's the delta that I assume the same for both, and I plus nj. And then there's my v and I and j. Okay, v depends on their before. This is really a copy of the formula over there, but now for these two atoms. So let me analyze this thing. And with the purpose of seeing how this, so there will be this effective interaction, and since v depends on r, that effective thing will also depend on r, but it will not be this r to the 6, it will be a different expression, and that's what I'm after. So let's analyze this Hamiltonian, take a basis, there you go, it's GG, GR, RG, RR. So my Hamiltonian is going to be a 4x4 matrix. Let me write that here. So on the diagonal I have 0 delta delta, and then I have 2 delta plus v. That's what these the one body and the two body terms do to me. And then I have all these omegas. Omega. Maybe let me take these two omegas equal to be a bit quicker. So both omegas equal to omega 2 or omega. Then there's omegas all over the place off the diagonal. So I think this is what that Hamiltonian is telling us. That's rather easy to see. And again, so remember that we're in a regime where the omegas are the small parameters, the deltas are quite a bit bigger, and then there's this v, which is the intra-atomic interaction. And so the task is now to go to that regime and figure, let's say, the lowest energy eigenvalue of this system, which will contain this v of r somehow, and will therefore be my induced effective interaction. So this is my h. If you look at this, I mean, from here it's an exercise again that you can probably all do. I'll probably add it to my exercise list so you can play with it. If you think about this, if you start from the top level, which is where you want to be, you do second order perturbation theory. You start coupling in the GR and the RG levels. So that's kind of this part of the matrix, which gives you an R independent term, because the R only sits here, right? The R dependent sits only here. So there's a slightly interesting second order perturbation contribution, but it's R independent, so it doesn't do much. If you do perturbation theory, you have to go to fourth order to actually reach this corner in multiple steps carried by omega. I mean, there's also other ways to do this, but in the end, let me give you what comes out. So the effective interaction, let me call that W of R, if I take the leading term of that, it has 4 omegas, because again, it's 4th order. If I stop at 2nd order, I miss the effect. Then there's a V of R on the top. And then downstairs, there's an 8 delta to the 3, and then a factor 2 delta plus V. So again, this is an exercise that you can do, and this is what comes out. But let me make the picture that's what this is all about. So yeah, I can put it in this corner. If I plot my W of R as function of R, remembering that V of R goes down like 1 of R to the 6. So this thing, is different than that. For example, if I send R to 0, my V goes to infinity, if you wish. But that simply means that my W reaches a constant factor. It doesn't blow up. So I have some limiting value, which I think is, this value over here is omega to the 4. You can see it from here. Over 8 delta to the 3. So that's the set of value. And then what you have is this kind of tabletop times potential. So you get this kind of shape. So the tail is set by this V of R, obviously. But the thing is a very different shape than the bare interaction. Okay, so and this is a characteristic, effective potential, which is called the Rydberg-Drast interaction, that you can play with. So if you bring atoms in this situation, so ground state Rydberg atoms, you do, illuminate them with an off resonant laser that has strength omega, you induce this interaction on the ground state level, which is way stronger than the van der Waals interaction on the ground state level. So this would be your dominant force that would determine how experimental things would happen to you. Okay, so you see this is a very rich system. So summarizing, I have this stressing regime that I just explained. I can facilitate, and then I'm like in this middle regime where certain states are forbidden, and I have this blockade regime where I'm blocking the nearest neighbor Rydberg state. And so you can imagine if you set up lots of atoms, you can play with the regime you go for, and you can observe dynamics. I'm not sure if I'm overlapping here with Subir Sachdev. He's on quite a few papers exploiting this situation and doing beautiful physics. I'm not sure if he brings it up in his lectures, but it's certainly one of the nicest tools we have these days to do quantum simulation with very well-controlled constituents and exploring nice and novel dynamical regimes of many-body physics. I think that's a nice moment for me to end. Also, the clock is about close to 12. Are there questions still from somewhere?
Yeah, there is one here, I see. What is the expression written on top of the tail? Omega? Okay, so maybe it's...
So which...
I guess it's for W of R.
So sorry, the graph that I'm putting here is this effective potential W of R, which is the same thing that I'm putting here as a formula. So it's the Drast interaction between the Rydberg atoms. And this arrow here indicates the value, the offset at R equals 0.
Okay, thank you. Other questions from the students? You can write on the chat, and then I will report to the speaker. No? Okay, so if there are, there is one. Is this a nice framework to simulate QDIT system then? This one.
Yes, so the QDIT aspect. So again, everything on the blackboard right now assumes a non-degenerate G. And so if you wish to view this as a qubit story, it would be the GR as a two-level system. But as I said, I'll probably have more on that tomorrow or on Monday. If you imagine a split ground state, that can act as your information carrier. And strontium, as a fact, comes with a 10-fold degenerate ground state. So that's a perfect incarnation of a QDIT system. There's actually, I was on a paper recently where we compiled a certain quantum algorithm, some graph clustering, and we went all the way working out how that can be implemented on this particular strontium QDIT system. And we argue it's a faster scheme than doing binary coding using qubits. So.
Then this WR is active in the RR subspace only or in GG as well?
So the W potential?
Yeah.
Yeah, so what happens in this regime is that your atoms are essentially all the time in the G state, with a very small amplitude to find them in the R state. But since they do have this virtual occupation of R, they have this interaction. But the idea of this whole scheme is that to keep the occupation of these three states essentially close to zero.
Good. Thank you. Other questions? Okay, so if there are no other questions for today, I think we can close here, and thanks to everybody, and see you tomorrow for, no, tomorrow is Saturday, no, so sorry. So see you next week for, yeah, this afternoon, but with Kareljan next week, I think, no? There is
Yeah, I can come to the discussion if you wish.
Okay, no, then there is a discussion session also.
Okay.
Okay, so see you later. Thank you.